Thank you, and thank you for coming to this talk. The talk is titled Microservices at Netflix Scale. We'll talk about the various definitions of microservices, and we'll talk about Netflix Scale. But first, I'd like to start with asking you a question. Did anyone make a large purchase recently? A house, expensive car? All right, so a few. How many of you made that purchase just looking at the features, the benefits, and not looking at the price? All right, good. So the analogy here with microservices is clear. It's in many talks and many seminars you go, microservices pitched purely for their benefits. But that's only one side of the story. These benefits come at certain costs. And so today what I'd like to talk to you about is Netflix's journey to microservices, benefits, I'll reiterate some of them, costs, lessons learned, basically the best practices and anti-patterns we discovered through our journey to microservices, and some resources that I'd like to make available to you. First, by way of introduction, Netflix, with over 81 million subscribers all over the world, we're probably the largest internet television network. And we allow people enjoy over 125 million hours of TV each day. That translates to a lot of bandwidth. We'll talk about it later. What I do at Netflix is I run several teams under the umbrella of platform engineering. We effectively make the Lego blocks that all the rest of the engineering teams at Netflix use to build their own applications. So we create that common layer to enable teams to move fast. Netflix runs on microservices. That's a well-known fact, but what is Netflix Scale? So 125 million of hours watched per day translates to over 4 billion hour streams each month. In other terms, it translates about 1/3 of North American downstream traffic on average. That's a lot of bits. At any point in time, all this traffic is supported by over 500 microservices. The reason I say over 500, simply because we don't know how many services are running at any given time. At any given day, we have maybe between hundreds to 1,000 production changes. New services are being deployed, existing services are being changed, some services are being retired. There is no central system that gates it all, because we want people to be able to move fast. All these services, we have an aspirational goal of 4 nines of availability. The more closer to reality will be 3.5 nines of availability, and we'll talk about that. And that runs across 3 AWS regions, 2 in North America and 1 in Europe, across 9 availability zones, and we'll talk about why. All of that, on a people side, that effectively represents a company of about 2,400 people. About half of them are technical, so about 1,200 engineers working on all these services. So let's start with the journey. How did we get to this point? Because we weren't always in the cloud, we weren't always in microservices. First of all, our journey took 7 years. It didn't happen overnight. We started back in August 2008 and just finished earlier this year. So it was a long journey. And our journey to microservices was not really a necessarily journey from monolith to microservices per se. It was triggered by our need to move into the cloud. And for various reasons, we blogged and talked about it at numerous places. I'm not going to reiterate there. But effectively, the only way for us to take a very big, complex system and take it from data center into the cloud, we couldn't just forklift. We couldn't just take this big, complex, fragile system, move it to the cloud, and say we're done. We had to chisel it piece by piece, effectively microservice by microservice, and then deploy it in the cloud. Re-architect it, redesign it, re-implement it, and put it in the cloud. So what did it look like before? In our own data center, we had a monolith. There was this application that all the various teams contributed jar files. It would get baked into a WAR. That WAR file would go through your normal bi-weekly test release cycle or the release train cycle, and then eventually get deployed. And on On a database side, it was a pretty big RDBMS, Oracle DB in particular, that would take all the traffic. And you can clearly see what the problems with this are, besides the velocity. We'll talk about velocity separately, but even from reliability perspective, this is very fragile. Any issue that you introduce to your application, whether it's instant or latent, will be homogeneously represented throughout your farms. So if you put a bug into one machine, you put a bug into all machines. In addition, this database does represent a single point of failure. So in the previous slide, I mentioned August 2008. This is exactly what happened in August 2008. We had a database failure. Our main production database got corrupted. And all of the Netflix users, most of them were not streaming at the time, they were still mostly getting DVD by mail, got this ugly message. Sorry, we're working on fixing our problem and we'll get back to you. That took 4 days. Imagine having a 4-day outage. That's not pretty. So that was sort of a triggering event that led our transformation into microservices, that led our transformation into being in the cloud only. And I'm really happy that transition is done. Before we get into the application and practice, let's talk about the first principles, effectively the assumptions that we all made. Once we started chiseling away those microservices from the monolith application, we had to make certain assumptions. We had to prioritize for something. So let's quickly go through what those assumptions were, and we'll also talk about why we made those assumptions. Because again, depending on what you're trying to optimize for, the assumptions could be different. And I didn't want to pitch you a particular solutions or frameworks without understanding first what those assumptions are. So first of all, we really don't like NIH or not invented here. If we faced with a choice between building something or buying something, and just to be clear, buying it doesn't necessarily limit us to a vendor software. It means just using off-the-shelf open source software. We prefer not to build it. If we can leverage and potentially contribute to something from open source, we would rather do that. And so we only reserve building something in-house for the cases where there is no other solutions for that will work for us. Particularly with our scale, we've tried many solutions that unfortunately ended up not working and ended up building a lot of our own software anyway, but at least we tried not to. Most of your services, as you break out your monolith, should be stateless, with a caveat, of course, except for persistence and caching layer. What that means is you shouldn't rely on any sticky sessions. If any particular instance or node dies, you should be able to simply retry it, hit a different instance, and proceed on with your execution. It's not enough to say, sure, okay, we'll do that. You have to prove it. And the way we prove it at Netflix is by chaos testing. Chaos Monkey and alike, we'll talk about that. Scale out versus scale up. You have two choices when you need more resources. One, you can go to instances or nodes with more resources, whether it's CPU, memory, storage, network. You can always get something that has more until you can't. Until you're running on that instance that has the most cores available, that has the most disk available. And what do then? You architecturally paint yourself in a corner. So what you'd rather do is when dealing at scale, you want to scale out. It's so much easier to add new instances. And especially in the cloud, because it gives you that nice benefit of elasticity. Not infinite elasticity, but elasticity nonetheless. Redundancy and isolation. We'll talk about it when we talk about resiliency, but it's really important. And these two principles are really common sense, but redundancy, you make more than one of anything. You simply don't want any single points of failure. Even though you make more than one of anything, you still need to isolate the blast radius for even given failure. Even if you have 150 nodes in your cluster, if one of the failures can result in cascading failure throughout the whole cluster, you haven't isolated that failure. And so it's important to do that. And of course, the destructive testing. What you want to do is you don't want it to be a one-off. You don't want to just do it once a quarter, once a release, or once whatever cycle. Like, you want it to be constantly running. You want to constantly prove that your system can withstand the failures that occur. Now, it's not if the failure occur. Failure will occur. It's when it will occur. And chances are, Murphy's Law still working, last I checked, failure will occur in the middle of the night, on Saturday night, where most of your engineers are asleep or drunk or both. And that's not the time when you want to wake them up and have them to deal with a failure. And so we actually put a lot of thought and practice into running destructive failures all the time during the office hours, where engineers are there, they're caffeinated, they're fully alert, they can deal with problems right away. So it started with Chaos Monkey, probably our most famous member of the Simian army, but it actually grew into a much bigger thing with the whole principle of being able to destructively prove that our systems are resilient. So how do these first principles, all these assumptions, work in action? Well, we talked about stateless services. In our ecosystem, in order for a stateless service to be a good citizen effectively, it just needs to do a few things. It needs to register into service discovery. And depending on your ecosystem, service discovery may be anything. It could be DNS, it could be your own service discovery, anything. It needs to implement a externally callable health check. Again, whether it's your service discovery or load balancer or other external agent can verify that your systems are not just there, but they're actually up and running and they're functional. And in order to call other services, it needs to utilize that information it gets from service discovery of where the other services are located. Simple, right? Right, until it fails. So when it fails, all you need to be able to verify is that the calling service, in this particular diagram, service A, just needs to retry that request. Get a different instance of service B, get the same response, and then move on. In order to do that, you have to kill an instance of service B or introduce a network partitioning event between a service A and an instance of service B, and then verify that the results are the same. You have to do it in production. That's the catch. I've seen tons of instances where developers and companies claim that, yes, I've done this testing on my development machine or environment, I've done this testing in test or QA environment, and yet in production the systems failed in a different way. So if you really want to prove to yourself that your stateless services are truly stateless, do this in production. You don't have to do it overnight. You can build confidence, but eventually if you really want to do this, you got to do it in production. Chaos Monkey, I mentioned it already. That's what it does. It's effectively a monkey running around a data center, a virtual data center in our case, but data center nonetheless, and killing instances randomly. We run it Monday through Friday, 9 to 3, and each application is subject to it. Initially, it was just stateless only. Now it's stateful applications as well, and you can tune it. Basically, you can tune it from doing it infrequently, of maybe once a day, to if you're feeling more bold, more frequently, and see how your system reacts. Data. So I mentioned in our data center environment, we had this big RDBMS instances running Oracle DBs. When we started migrating to microservices to the cloud, we embraced Cassandra as our main key value storage, and for several reasons. One, it actually runs at scale. It's one of the biggest scale NoSQL engines. It's open source, and that was important to us because very early on we needed to, and we in fact contributed quite a bit to Cassandra in order to make it multi-regional, multi-directional replication ready. And in terms of the storage engine, from perspective of cap theorem, it's available, it tolerates partitions well, and it has tunable consistency. Now, in many talks about Cassandra, you'll hear that it's eventual consistency engine. That's actually only a part of the story. With Cassandra, per request, whether you're reading or writing, you can tune the consistency of that request. From CL1, which is pure eventual consistency, to local quorum, all the way to the global quorum. I don't recommend global quorum, and we'll go in those reasons. So this is actually how Cassandra multi-regional replication works. On one side, your client, let's say, writes with a local quorum. That means you're going to get 3 replicas locally within the region before getting an ACK, before confirming that the write has been made. But what you don't want to do is tolerate that confirmation over the long distance network across the regions. Your reads and writes simply will be too slow. It's not going to scale. So what you want to do is you want to replicate that data across regions asynchronously. And that's actually a change that one of our committers contributed to Cassandra very early on, many years ago, and now it's default in the distribution. So we talked about stateless services. We talked about stateful services. There is also issue of billing services, which probably composed of both, but they deal with money. So you have to be a little bit more careful. And that's the service that took us the longest to migrate to the cloud, to break into microservices, and for a good reason. We don't want to overcharge our users. We also don't want to undercharge our users. We want to do it just right. So also in order to be compliant with SOX and PCI in US, we had to put these services into a separate account with a limited access. It's not as fully open as all the other production systems at Netflix. It should be fully logged and auditable. And the key there is just to be a little bit more careful about what you're doing. Okay, so I will go very quickly through the benefits of microservices because I'm pretty sure you've heard many of them already many times, but I think that some of them worth repeating. But before that, what are Netflix priorities? What are we trying to optimize for? Well, first and foremost, we want to optimize for velocity, for innovation. For us, it's really important that all of our teams that are working on Netflix product move fast. And because of that, we're actually willing, and so far been able to sacrifice a little bit of reliability. That's why you see reliability is priority number 2, as silly as it may sound, in order to achieve that high velocity. And efficiency is only a third on that list. So when we're making this trade-offs, when we're trying to decide which way to optimize, we always optimize for innovation first. And that's exactly the challenge that you have in typical monolith systems and the release cycles of monolith systems. You have your teams that are producing various components. They're all developing. Eventually, they submit their development results into a test cycle for a trained release, and eventually, after the QA signs off, that gets released. That creates a lot of tight coupling between the teams, and that just doesn't work if you're trying to optimize for velocity. It's too slow. Loose coupling is when you have each team working independently. That means each team needs to now work all of the parts of the cycle. They develop, they architect, they design, they develop, they test, they deploy, and they support. In other words, it's end-to-end ownership. Now, in this, sometimes it's called DevOps model. I'm trying not to use this word because it's getting overused to the point of being a buzzword. But if you think of end-to-end ownership, your team is responsible for everything, from cradle to the grave. And this way, their motivations are set up so they write quality code, but they also write it fast, because engineers, especially great engineers, they're motivated by the results. They're motivated by the impact that they make. And if each team owns the full cycle, you'd get something like this, where all of them are constantly making progress. All of them are constantly doing something. If you think about it in technical terms, imagine each team is a thread, and all of them are running independently in parallel, without a single gate to block them, to impede the progress. All these teams that Netflix runs, they're very loosely coupled. We don't have a central place to gate or approve their releases. They each move on their own cycle at their own cadence. You also get the benefit of separation of concerns. For example, the lowest layer, the infrastructure teams that I work with, we're mostly concerned with availability, scalability, security, the fundamental qualities that each application should have. So then the teams who build their applications out of the Lego blocks that we provide don't have to reinvent that wheel. They can build on top of it and leverage what we already have done. Enough about the benefits, though. Let's talk about the cost. Nothing is free. First and foremost, microservices and an org change. if you want all your teams to embrace the full cycle, that means you no longer have necessarily a QA team. You no longer have an ops team. Now, who wants to hear that their job is going away or changing, right? These are the harder things. These are the people things. Emotions are involved. Org changes are hard. And so what you need to do is you have to evolve the organization over time, gradually. You won't be able to do it overnight. And just to give you a couple of examples of how your practices may change, again, depending on what works for you. In our data center environment many years ago, we had a centralized NOC that was basically approving and driving all the releases. Right? We had a IT group that was responsible for capacity and budgeting and planning and executing that capacity. We had DBAs who were effectively gatekeepers to these big RDBMSs that we had. We no longer have any of that. Now, if the developer or a team needs resources, they self-provision it through the tools. Now, because they do it through the tools, it's all transparent, everybody can see what's going on, and the people who concern themselves with capacity, they can see a real-time signal of where that capacity is needed. We don't have an ops team. We have a SRE team that builds centralized set of tools that everybody can use, leverage to operate their own systems, but they're not gating anybody. And the DBAs, they work with other teams to work out what schemas for their databases would be optimal, but we don't operate anything for anybody. So it's a lot of centralized teams who build the support models, who build the frameworks for other teams to enable them to own the full life cycle. Again, it's effectively we're building these Lego blocks. But in order for you to reap that benefit, you have to invest. You have to build the teams that will build these Lego blocks. Here comes the catch. You have to do it while still running your old stack. And because migration doesn't happen overnight, you're going to be living in this dual world for a while. And at Netflix, we use this term that this image represents Roman riding. That's when you ride two horses, one leg at a time. This guy looks very uncomfortable. Think about it. You supporting two tech stacks. That's double the bugs, double the maintenance. Sometimes you have to propagate new features in two places. You have to replicate data. And multi-master data replication, especially at scale, is no picnic. No matter what great engineers you have and how much testing you do, it's not going to be foolproof. And only once you switch over the source of truth to the new state and stop that multi-master data replication, you will be able to breathe a sigh of relief. Until then, you're going to be constantly fighting some kind of battles. So what kind of lessons we learned through that journey? First and foremost, that there are a few pieces that are critical to ensure this loose coupling. Now, you talk about loose coupling between the various teams developing microservices. There are really two pieces that are needed. One I covered on the slide, which is IPC or RPC, again, interchangeable terms. But you effectively want to establish a contract or a language between any two services to talk to one another. This way, when time comes to develop a new system, you already know which language to talk to all these systems. And if you have 500 plus microservices running, you don't want to know 500 different languages. It just simply doesn't scale. So IPC is one of those pieces. The other one, equally as important, you want some homogeneity, you want some consistency in how your applications are being deployed. For us, initially, it was Asgard that we had to develop in-house, and then we recently replaced it with another tool that we also open source called Spinnaker that automates all of our deployment workflows. The benefit of that being, again, the same central tool is that people don't have to reinvent this wheel already, and we also get a source of truth point of view from what applications were deployed when and how. And that provides an invaluable insight in a time of crisis. One of the first things you want to see when something goes south is what was changed most recently. Databases. It's one thing when your database gets called by 1 or 2 monolith applications. It's completely different when suddenly it's get pummeled by 500 plus microservices. You want to protect your databases. And so a pattern that we evolved into over time is that for our most heavily hit databases, even Cassandra has its limits, we protect it with a layer of cache. And so we use actually 2 different caching technologies within Netflix. One is the key value add-on we build on top of Memcache called EVCache. And the other one is a richer schema that you could use Redis for. It is called Dynamite. But the idea is the same. What you want to do is on the read path, you want to hit cache first and go to database only on a cache miss. And if you go to database on a cache miss, on the way back, you're going to backfill the cache. You also want to make sure that in your call graph, right at the top of that call graph, you will have a certain request cache. So then, for example, if in the beginning of that call you had to fetch the user information to understand some metadata about that user, you will propagate it downstream so all the subsequent services don't have to go and call that database again to fetch the same metadata over and over and over again. You will find that you will reduce the load in your databases by at least 1 order of magnitude, maybe 2, maybe 3. It depends on your call graph depth and interconnectedness. Telemetry. Operational visibility matters a lot. If you run your monolith, you probably have some good metrics of what kind of application and system metrics you're looking into to understand your system's health. When you run hundreds of microservices, will your telemetry scale? How many graphs are you looking per server? Multiply it by number of microservices that you have. Will you be able to see forests from the trees? Per server, how much individual human action is needed when something goes wrong? How much of that are you able to automate? Just to give you an idea, at Netflix we generate over 20 million metrics a second on average. That translates to about 1.7 trillion a day. That's simply unsustainable for anybody, any human, to look into all of those metrics and actually be able to get some signal from that noise. And so most of these metrics never get looked at least by a human. They get piped into automatic automatic error detection algorithms. They get piped into automatic remediation algorithms that will detect if there is an anomaly, and in many cases will correct it without human ever being involved. The same goes to your log analysis tools. Right? If you generate logs like us, I mean, a couple of years ago, my ex-colleague coined the term that Netflix is a log generation service that also allows you to watch movies, because we just produce such an obscene amount of logs. And so you need to be able to find and hone in tools that will allow you to get that signal out of all that noise, and preferably automate as much of it as you can. So this is what it looks like. Once you get into this scale of microservices, you simply don't have a luxury of having architectural diagrams, because things change all the time. And so what you'll need is a runtime. At runtime, you need to be able to discern who's calling who, how, where are the errors, where is traffic flowing, is there any congestion into a system. It may look something like this, it may look something different. In this particular case, you see that traffic starts at the elastic load balancer for us. Then it gets spread through our front line of defense called Zool, which is our front-end proxy. Then your calls may go into playback systems, API backend, and this area comprises our edge systems, this kind of front line of defense. From then on, you have middle tier services, platform services like caching and databases, and so on and so forth. But this type of insight, this type of telemetry, you have to generate at runtime. Because if you just create a static architectural diagram, with the next service push is going to change, it's going to render it obsolete. Reliability. It matters a lot, especially at scale. Failure happens in distributed systems, and the rate of failure is proportional to the amount of change that you're pushing through and the scale at which you're running. For us, both are massive. And so we strive, aspirationally we strive for 4 nines of availability. Unfortunately, that only leaves us 52 minutes of downtime per year. Up to now, we haven't been able to consistently achieve that. Now, and when Netflix, these days when Netflix is out, that causes some disappointment. Outrage. Or withdrawal. Luckily, some people actually do retain their sense of humor and react a lot more positively. But availability is important. As much as we'd like to focus on innovation and velocity only, you can't do it, at least for long, if your system becomes unavailable. People just stop using it. Now, in distributed systems, especially when you have a large number of microservices, you have to face the fact that you'll see some cascading failures. If you test each individual service, microservice that you write, and each individual service reliability is 2 nines, well, it's not great, but it's not bad. But if your graph is fairly interconnected and you have over 500 of them, the total availability is not going to be very good. In fact, you're going to be out of service most of the time. That's not acceptable. So what you want to do is you want to detect and correct these failures as fast as you can. Thus comes the whole concept of circuit breakers, because circuit breakers detect a fault in your electrical systems and trigger a fallback. In electrical systems, you simply switch the power off. But in software, we have more options. If you detect a failure in a downstream system, what you don't want is that same failure to be propagated eventually to the client, because that's not very helpful, even if you propagate that failure fast. What you want to do is you want to detect that there is a problem and figure out whether the problem is with a critical service, in which case, game is over, or a non-critical service. And if it's a non-critical service, like for example, at Netflix, it could be a personalization. Maybe for whatever reason, we cannot give you the level of personalization that we like to do. Well, you still can probably would enjoy browsing and selecting from a set of movies and TV shows that's not necessarily personalized to your maximum liking. Probably will still find something good to watch. So what you'd like to do, you want all those failures to turn into fallbacks as immediately as you can. And this way you can still operate while the team responsible goes to debug and fix the problem. So a few years back, we actually open sourced a library that enables us to do just that. It's called Hystrix, and it's been used by many companies. We've been getting really good feedback and contributions of that. I can't emphasize this enough. You have to do destructive testing. Failures will happen, and you only know how your system will react to that failure if you inject it. You got to do it in production. Again, not to start with, but eventually, if you want to prove it, you got to do it in production. Because failures happen not just at the system or cluster level, but across those clusters at the network level. Some failures are more insidious than others. If something fails, it's actually a lot cleaner. You know it's broken, you know you're getting error or mangled response back, you can deal with it. It's a lot more insidious when a response is returned just too slow, too late, right at the point where it's going to trigger your timeout. Imagine it could cause cascading timeouts. That's just not a pretty scenario. And so we actually develop a system internally known as FIT, where we're able to inject per request in individual call path certain faults. And the faults could be errors, or they could be latencies, or combinations thereof. And when all else fails, you gotta trigger failure on more massive scale. It's not enough to trigger failure in individual instance, or zone, or even full cluster. At Netflix, we actually trigger failures, exercise it in production, on a monthly basis at least, for our full regions. So all of our services run at 3 AWS regions across 9 zones. At least once a month, we randomly select one of the regions, and we evacuate out of it. We basically simulate that if that region would fail, what would our users see? And our goal, which happily to say right now is the case, when we evacuate out of a region, as a user, you will not see a thing. Netflix services will continue working as if nothing happened. It wasn't always like that. The first couple of times we ran the simulation, we call it KSCon, things were not as fun. We had about 40 engineers in a war room scenario, debugging for about 4 hours, trying to figure out various things that went wrong. And then we fixed those things, and we tried it again. And then it was 10 engineers debugging for about 2 hours. And now it's effectively a piece of automation, a piece of script that runs at monthly intervals. Most of engineers don't even know when it runs because the results are so transparent. It takes a while to get there, but once you get there, the rewards are pretty damn good. So that's the graphs of us, in this particular case, evacuating US East into US West and EU West regions. You will see that on the bottom, as the traffic went out to the other regions, the overall traffic did not change. Or, as this much cooler illustration shows, this is what a lot faster timescale replay of what exactly happened. The traffic that you see emanating from the middle circle is the traffic from our users from the internet. The traffic across the edges, that's the traffic between the regions. And you will see that right now we triggered a failure in this region right here in US West 2. It turned red. And we just started proxying traffic to the other 2 surviving regions. And as that continues to ramp up speed and scale, at a certain point, we will flip DNS switch, and you will no longer see any traffic hitting US East, US West, because all the traffic had been fully redirected to the other regions. This is a big hammer. Takes a long time to get there. But if high availability is your goal, you're going to have to exercise something like this. Not necessarily this. It's whatever works for you. OK, no talk on microservices would be complete without mentioning containers. It's latest and greatest. It's very shiny. But let's get down to basics. Containers don't make microservices. Containers change the level of encapsulation, of isolation, from virtual machine to a process. Containers bring you great benefits, specifically for developer velocity. You can iterate on a second-length cycles. You get the same artifact that you run on your development machine, the same as in production. You can do a lot of really cool magic with containers, as actually the first talk this morning showed. But it's not a silver bullet. And so make sure that you're using it because it's the right tool for the job. Besides, to run containers at scale would require something like this. This slide is intentionally meant to be an information overload. I'm not going to dwell on any details here, but it does require a very significant and complex systems. Now, Google has done amazing work with Kubernetes. It's matured quite a bit over the last couple of years. If you're thinking of containers, use foundational blocks that are available to you. Don't write your own. Unfortunately for us, we started a bit earlier where a lot of these blocks were not available or were not available at our scale. And so again, our preference is not to build something we can buy. In this case, we actually ended up building a lot of pieces. In our container runtime called Titus, we had to write our own custom scheduler and a whole bunch of other things simply because the ecosystem was not ready yet for our scale. So let's talk about some resources that are available for you, or you can think of it as a commercial break from the regularly scheduled presentation. Because by being pioneer into the cloud so early, we ended up writing a lot of things anyway. And because we ended up writing a lot of these kind of foundational pieces, we open sourced them. And so they're available to you. If you go to netflix.github.com, you will find most of our infrastructure pieces, the tooling pieces, that are available to you to use and contribute if you choose to. And they separate into major categories, so it should be fairly easy for you to find anything that you're looking for. Don't try to read the small print. You can just go to the site, and it's all there. But the main pieces that you could benefit from, Spinnaker is the tool that we open source that works for continuous delivery workflow deployments consistently throughout any your stateful or stateless applications. For the common runtime sharing libraries, if you need service discovery, for example, we have Eureka that you could use. There are many other alternatives as well. And there are a few IPC components there as well. For data persistence, we open source and contributed components to Cassandra ecosystem, components to Redis ecosystem. If you need to make Redis distributed, we have the component Dynamite, EVCache for the Memcache client replication and such. For Insight, again, if you need telemetry for distributed systems at scale, large pieces of it are available. You can plug it into your ecosystem. Security matters a lot, and probably the last thing you want your teams to keep reinventing is security pieces. It takes some skilled security software engineers to write good crypto, to write good secure systems that will not fall down under basic attacks. And what you'd like to do is to provide these either as services or shared libraries so your application engineers can focus on the application logic. That's their business impact. It's not reinventing security. So to wrap up, microservices are good. They bring great value to development velocity, availability, many other dimensions, but they're not free. Microservices at scale, first and foremost, requires organizational change and centralized infrastructure investment, if you want to do it right. And it's up to you when you want to make that investment. Just keep in mind that if you have 10 teams working on 10 microservices and you want to introduce a certain centralized change, there's this much amount of tax that all 10 teams will have to pay. If you want to do it later, and perhaps there's 200 teams running 200 microservices, your centralized tax becomes a lot larger, and so optimized accordingly. Also, I can't stress this enough, don't do something just because we did it. What worked for us may not work for you. So be aware of your situation and what are the right trade-offs optimizations for you. We're happy to share our tools, but they'll only work for you if you're making the similar assumptions and similar trade-offs as we do. I hope this was helpful. I can take any of your questions now.
Thank you very much. There are some interesting questions from the audience, and actually one of them caused a little smile on my face. Analog to the falling tree in the forest, if Chaos Kong kills stuff and nobody notices it, how do you know it actually happened?
Excellent question. So just because our users may not be aware that Chaos Kong killed something, our telemetry is. We have telemetry and logs in obscene amounts that pretty much tells us everything that's happening within our system. Now, of course, the most obvious side effect that we never want to see, but we've seen it from time to time, is when Chaos Kong causes user impact. But this is actually a failure that we can learn from and make our systems more resilient. The tougher situation is when Kong kills something and users don't see anything. It actually takes discipline from all the system developers involved to look at their log of their system health, understand how the systems fared under the evacuation situation, under the latency situations, and make sure that there is no bottlenecks that we're close to reaching, that there is no failures that we just degraded out of and everything seemed peachy, but it wasn't. So there is a little bit of follow-up that happens internally, but first and foremost, of course, when we run Kongs is that there is no user impact.
And who or how do you decide what services and thus teams need to be created or go away? Is that a central architect or?
Excellent question. So we don't have a central architect. We don't have architectural committees. We really try to embrace culturally this whole concept of loose coupling and individual, or in this particular case, team freedom and responsibility. So each team is free, but also responsible for making these calls. When new services need to come into operation, when certain services need to be retired, and how to deal with the migration strategies.
I think someone is afraid to do the chaos testing in production, so I think that's why this question came up. Would you also recommend destructive testing on production on more critical applications, for example, financial? Again, it depends what you're trying to optimize for. It's a really good question. But at a certain point, you need to embrace the fact that failure will happen. And if you don't test it, it's going to happen anyway.
What you're gaining on running the destructive testing, and yes, in production, is your understanding of whether your technology is ready to deal with these failures, but more importantly, are your people ready to deal with these failures? For example, will they have runbooks, or will they have to scramble? Do you have enough people who understand your systems? Do you have enough people who know who to call, who understand these systems? This readiness, you can do simulation, you can run the drills, but nothing beats running it in production. And if you want to do it in production, but on a copy of that, let's say, because it's your billing system in a shadow mode, that's fine too. But you want to get as close to the real thing as you're comfortable with. Please don't do it just because Netflix does it. We got comfortable with this over years.
So to do a fire drill, you don't really need to put the building on fire. That's what you're saying.
Probably not, no.
A question that has popped up more than once, so I really have to ask that. Where can we get those awesome service visualizations?
So the service visualization that I used here in videos are called Flux and Flow. They haven't been open sourced yet, but I use the keyword yet because our philosophy is generally we want to open source anything that's not proprietary or critical to the business, which these as pieces of infrastructure are not. We'd like to share them. At the same time, I can't commit on behalf of those teams to any particular timeline because business priorities always come first. All I can tell you that we'd love to open source them, we'd love to share it with you and actually get your feedback and contributions. I just don't know how soon or how not soon it's going to happen.
I guess we have time for one or two more. What kind of discipline do you ask of your team members?
Oh, that's a loaded question. Nothing really in particular, but if you haven't seen our culture deck, I highly recommend you go see it. It's available on SlideShare on our site. If you've seen it, this whole concept of freedom and responsibility, the type of developers that are hired and become successful at Netflix really embrace it. And it doesn't mean that these people don't make mistakes. It means that they learn from their mistakes. Mistakes are fine. I mean, that's how we learn. You just don't want to keep making the same mistake all over again.
Okay. Last question. Services belong to teams. How do you handle new functionality that needs change in many services? Is there something to manage this smoothly?
Yes, and it's one of those hard situations where there is no magic bullet. There are cases, especially with security. Let's say you want to respond to a newly discovered threat, or you need a critical piece of functionality to be spread throughout all the services, where a centralized campaign is necessary. And you need somebody to coordinate it. Most of the time for us, this is basically the team that is pushing the change, the championing the change. They go and cross-functionally interface with whoever required and make that change get into production. Because most of our teams do implement some sort of CI/CD, where even centralized library changes get pushed on a regular cadence automatically, it really becomes a question of long tail. There will be, no matter how much you try to embrace continuous delivery, there will be a subset of applications that are not pushed as often, and those will require special attention.
Okay, that's it.
All right.
Thank you very much, and
Thank you.
please make sure that you vote for the session.